Okay, so we're just gonna try to extract. Extract might not be the right word. We want to build up. We've already built up the put function. We want to build up the get function, and then actually use them and write the tests for that code as well. And then we're gonna be done for today because I'm kind of sick of this. And but I always want to try to make a little bit of progress every day. So even though I am sick of this, and I really don't want to work right now, we're going to just try to get some stuff done, right? So, with that said, let's edit our thing here for a second, and let's remove the camera thing, and just say this. Today is a boring day. Ask me anything. That way we can kind of switch to, you know, playing some music or whatnot and just trying to get through this. So, yeah, because I really don't, yeah. Yeah, let's just open something up, and then we'll just get going, right? Alright, hold up here. So I realized that, while I was doing this stuff, I was muted. And I was trying to explain things and I was muted. So that sucks, so I'll have to fix that. But one thing, I'm in the middle of something. I'm downloading some more music here from Overclocked Remix. So, let's see, music. The year is 2021. So I'm going to download some music here. It's going to take forever, it seems, because my connection speed kind of sucks here. So yeah, I was looking for the order of RGB and A, and I was kind of looking at it. So if you see in our commentary, we're searching for RGBA in the source code, and you can see RGBA is here. RGBA 8 UI for unsigned integer texture, RGBA, right? So everything is RGBA as far as I'm concerned. So make a note here that, you know, RGBA is the order. So I'll take this and run with it. Okay, so these will be my shortcuts for the next time I have to ask this question. But for good measure, we also should see, well, what happens if I search for the opposite, the ARGB? Do we find any mention of that in the source code? So let's take a look here and just go ARGB and see if somewhere in the files I'm using this. And possibly I'm using it incorrectly. So it's only on one place. It's actually in load PNG, which is not my code. So I'm confident that we don't RGBA. Yeah, I'm confident, and also it's not even that, right? Because this A is from the other one. So yeah, there's no real reference to ARGB. That's the thing from like Macromedia Flash. Flash used to use that kind of arrangement of pixels or bytes within a pixel. So now that I know that's all right, let's look at this little timestamp over here, because we were explaining something, and then we realized, oh crap, the sound was muted. So let's explain this right now. So the time right now is 1 hour, 21 minutes. So let's say 1 hour and 21 minutes and 40 seconds, we'll say. Okay, so update that. Okay, use GlowCom to extract the current pixel we are looking at. This is not the way we want to do it in production because we are looking at 4 bytes when we only need 1 of them. However, the math is more straightforward this way and better for unit testing. Yes, so the way we've divided the data, if we look at the PAINT5D data, every single value, every single 2-bit value that we're packing into a pixel fits neatly within the red, green, blue, or alpha bytes. And because of that, we don't have to extract an entire pixel's worth of data and then shift out one of these values. We can actually extract either this, that, or that, and shift out the value from there. So we only have to actually look at 1 byte, not 4. However, because we are writing test code, it's a little bit more straightforward to extract an entire pixel, an entire uint32, and then to shift out the value from here, right? So we'll take this pixel value, we'll shift it based on the offset dex times 2, right? Because there's 2 bits per every single tile value that's encoded in here. And the offset dex goes from 0 to 15, right? So this is how we're kind of partitioning these bits here in this diagram. And we need one AND symbol. Make sure that's one AND symbol here. And then we're going to mask it with a binary 1-1. So this 3 is binary 1-1. And if everything goes all right, then this variable here should be equal to the tile value that we set up here. And if it doesn't go right, then, well, we'll have a problem, won't we? Okay, so for the for this, what's going on here? Putting 0 should revert the entire test array to all zeros. Okay, cool. So if we put 0, we're going to expect that it erases things, right? So we're going to put 0, and then we're going to loop through the entire mock array of pixel data. We're going to loop through the entire thing and check each byte index and make sure that's equal to exactly all zeros, right? Because we should have zeroed it out by now. Okay, so now that we've cleared that up, let's look at the next thing we want to do, right? So we have this test table, and that's all good, but one of the problems with this is this isn't going to catch any like accidental overwriting from passing in multiple values or packing multiple values into the same byte. So I think we need another table. So I don't know. I guess we could go down here. And is this a for loop, or is this just some code where I didn't write? Ooh, that's bad. So somewhere in here we kind of screwed up our indentation here. Right? We can see that this is kind of something is missing. Something is wrong with our braces. Our braces aren't properly paired. So this for loop, do we ever end this for loop? Because I'm going to guess that would be, well, supposedly this is the end of the for loop. This is another for loop, right? So everything looks kind of in place, but we obviously know it's not. Oh, so this is not correct. So first of all, this is all bogus. So first of all, it needs to be like that to close it off, and then this actually needs to be a function call, right? Now, I really don't want to make this more verbose than it has to be, so, well, too late. More verbose than it has to be, taking up more room than it has to, but whatever, there we are. Okay, so now if we look at this, do our braces line up? Because that looked like the mistake. Yeah, so that looks like the mistake we made. Okay, so now we want, like, another test table. And we'll take table, we'll just call it table 2, right? So we'll say U8 table 2 and some number times some other number equals, and then some stuff here, right? And for this, I guess we have this, so we should probably just label these as like 001 and then go up to where this is, right, and just say this you're now number 1, right? Because we have 2 test tables in here now, and then where we're actually adding these, multiplying them together, right? We'll do this, and we'll do that, and then over where we need the maximum index, same deal, make that number 1, and then after we've kind of used that everywhere it needs to be used, we can create our second set of defines for the next set of tests, right? So we're going to just label this 2, and we don't actually know what these values need to be yet, so we'll blank this out. Test table number 2. Right, so this is test table number 2 sizes, is what this is. And we can reuse a lot of the variables we were working with, but what we really want to do here is just say, I'm thinking that if everything worked all right there, then what we really care about is just kind of setting down like 15 values or values that are next to each other. I guess if we set down, the best test would be setting down kind of 15 values and doing that multiple times and just seeing what happens, right? So I think that what we want here is we want something like, you know, we just want to label a series of 15 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, and also the index is 1 based. So do we have just enough room? It looks like we have just enough room, unless I was making some things up and something's missing here. But let's set everything to 3s for a second. So, set everything full, right? So, all 3s. And we're going to expect to be able to fetch these again. And I guess 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, 16 slots total. That's how many we need. So that is correct. So yeah, let's just do a run line kind of sequence of 3s, 2s, and 1s. And after that, 3, 2s, 1s, and 0s, I guess. 0s is kind of pointless in the sense that I don't think it's going to help me find anything, but, you know, for consistency, we might as well. And also, I have been shocked before with how I didn't think something would actually give me any extra information, and it actually did. So we'll do something like this first. And then we'll try to be kind of more interesting, right? So we'll try to say interlace something, do something interesting. I don't know what we want to do. It doesn't really matter. It just matters that we have some type of pattern. So let's try like a 0, 1, 2, 3. Right, so 0, 1, 2, 3, 0, 1, 2, 3, etc. And how about 3, 2, 1, and 0? How about trying that? And there's a lot of things we could try here, right? We could try 1, 1, or actually 0, 0, 0, 0, right? We could try a whole bunch of zeros in a row, and I'm trying to make sure these are correctly aligned as well, right, in this table, right? Because this is basically a table of data, so we want to keep the alignment correct. Oh yeah, why not try something like this? Okay, and 0, 1, 2, and 3, right? What else could we try that could help? Well, let's look at these borders here. So the borders here are kind of telling me that that the problem, I'm thinking the problem is likely, if there is a problem, spanning these gaps would be something I might want to look for. Now, the way we've grouped this, right, we actually do have different values spanning those gaps, so that's good. Let's try something like maxed out values interlaced with zeros, right? And then interlaced the other way as well. So we take this and I think right, so interlacing it the other way. Now for this 0, 1, 2, 3, why not do the inverse of that as well? So, right, try to do the symmetrical cases. It's not, I don't have any logical justification as why to do symmetrical cases like this. It's just kind of a hunch that doing things symmetrical like this could help catch edge cases. If it's an edge case this way, then the opposite should probably also be an edge case. That's just that is a wild guess, there's a probability that if it's an edge case and we flip it, it's also an edge case, right? Because minimum and maximum bounds and whatnot. But that's totally a guess. So we have a decent amount of things here where I think if this works, I'm pretty satisfied. Now, we might as well kind of, for good measure, be like, 1, 3, 2, and just kind of like pick values here. Like, let's just mash the keyboard a little bit with the correct numbers. Right, so let's mash the keyboard, with the correct numbers. And then let's just insert commas where they need to be. And then we'll see... We'll just... I think we'll do this for like 2 rows, right? So we'll try to do this twice with just kind of button mashed values. Because, you know, by putting in these very precise kind of patterns, that might not trigger an error because something about the symmetry of the patterns could be doing some type of coincidences that make no errors happen when errors should happen, if that makes sense. So we're going to mash some more numbers. And yeah, we'll do just 2 cases of just having mashed together a whole bunch of numbers. And the reason why this case is going to be last is because we really hope that we don't have this case fail us. Because it's going to be easier to comprehend what's in here when we have these very regular patterns. When we have this very irregular pattern, it's going to be harder to reason about the data. So using this as our last final test, I think, kind of makes sense here. So, you know, random number test, keep this one last, because I really don't want to deal with this test case failing as the lack of a order. Alright, so this is what's going on here. And we can make a note of where we are right now. So at vid IID, it's 1 hour, 35 minutes, and we'll say 25 seconds. We'll just make that 30 seconds now because we screwed up. Or maybe not, because this is not the integer ID. This is the integer ID, and the time is that. But now the time is not that. Now it's like, let's just put a 42 there. Okay. So, the last random number test here, or the last test here, the last test cases here, are just kind of random numbers just for good measure. And we want to make this test case the last test case, because we really do not want these last test cases to fail, because it's just going to be a pain to mentally reason about all these numbers, because we'll have to be like, right, to figure out where these different numbers are, we'll have to inspect, right, and count and whatnot, whereas with these more regular patterns, we can be like, okay, there's a cluster of 3s, here's a cluster of 0s, right? It's going to be easier to mentally reason about these tests than it is these tests. So we're going to hope that if there's any failures with these tests, that the failures happen here, we fix the code, and once the code is fixed, these will pass. That's what we're banking on, but it might not happen. So let's look at this. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got 12 tests. We have enough room to where we could kind of like keep a little checksum here, right? So let's do that. So we got, right, and it is kind of ugly this way, but having that checksum makes it really easy to look at the numbers we've hard-coded into those defines and make sure that they're actually covering everything that's here. So we're going to continue doing this kind of stuff just to make sure that we're actually executing all of the test code that we've actually defined, because if we don't, then we could create these big, large tables and then not actually iterate over them, and that would be a huge problem, because you would have this confidence that your code is actually working when it's not, because you didn't actually iterate through all those test cases. So 12 things. Does that make sense? So we got 4, 2, 2, and 2. 3 times 2, that's 6, and there's a 4, so that's a 7, and 8, 9, and so I did my math incorrectly. 4 and, oh, this is not 4 and 3, this is 4 and 6, and that's a 10, 11, 12. Okay, yeah, okay, cool. So now that we know this, that there's 12 things here, and this is 16, right? 0 to 15, so that's 16. So the number of elements in a single test, right? The number of elements is 16, okay? And the number of tests that are here is 12, right? We had 12 tests. And if we get this wrong, we'll either not test everything, or worse, we'll have seg faults, or somewhere in the middle, we'll be grabbing the wrong data. So a lot of things could happen if we get these numbers wrong. So let's try not to get these numbers wrong. So number of elements and number of tests. So down here, the number of elements for number 2 is 16. And the number of tests for O2 is 12. And we can actually double check this, right? We could do a little assert and be like, hey, the number of elements should be 16, right? And then we could do a little double check over here as well. The number of tests is 12. Right? The number of elements, the number of tests. Okay, cool. Now that we have that, what are we actually doing with this? Well, we're extracting all these values and kind of getting and putting them. So let's make another loop here. So let's just steal this kind of loop here, because this is what we're going to need here. And we can paste it down here. And from here, we can say, what are we doing here? We need to use the put command 10 different times, don't we? Okay, sure. So if that's the case, that's what we need to do. We can take this put command and think about, we could probably be a little bit efficient about this, right? We don't have to cut and paste this command 16 different times. This offset dex is, we can put this offset dex in a loop, and the global component here, we could set that to 0 here, right? We could set that to 0, and the tile value is what we're extracting here. So we could do like this, tile value equals, and take the test array number 2, right, this test table, and then we could use the offset dex, I believe, right? Not just the offset dex, we need the base value, right? And to calculate the base value equals the test index times number of elements in the second array. And now I already see a mistake. This max index needs to be the test array number 2, right? Okay, so we're going to loop through this. The base index is the test index times the stride, the number of elements per test. So when we get this base index, we offset by the offset index. And you'll notice that offset index, well, where are you coming from, right? Well, that is another inner loop. We're going to do inner loop for the offset dex this time, so that we can access all 16 elements in this really quickly. So we'll just say, I don't know if we want to indent this, but, well, now we have. So osdex equals 0. Okay, so if we do that, we're going to run out of room really quick. Let's just indent it this way for now. And, right, let's not actually indent this because we don't have much room. And yeah, so we're going to put it in this offset dex location. We're going to fetch it this way to get that value. And that will be the tile value, right? So we're going to set this tile value. And we're going to set this. So this is obviously kind of a weird way to do it. Now, after we put this value, do we want to retrieve it in a, so I think we want to put everything and then we want to get everything, right? Because we're trying to see if things are being incorrectly packed, right? Or like overriding values, like we're memory stomping things. So we actually do want this we want this like that, and then we want another loop like this, right? So we want to do another loop And this first loop is where we put everything, and the next loop is where we're going to get everything. And to get everything, so this should be, let's just call it expected val. Right, so this is the expected tile value. Alright, so same formula is the expected tile value. And to get the actual tile value, we already have the math for that, right? We have the math up here, we already did it. So we can copy this, we can kind of steal this and be like, oh, we got to zero it out, we got to do all that stuff. So let's just steal this. We didn't really need to zero it out like we did, but let's just, yeah, let's steal this and then take a look at it for a second. Okay, so this U08 variable is going to be ostex. Okay, so this is the actual value, right? So this is the tile value. Instead of using an expected value, why don't we just call it tile value, right? Because then we don't have to make up a new variable, right? So this is the expected tile value, right? Because it's in our test table. And this is actual. This is the actual tile value now, right here. This U08 var. Okay, so yeah, so we're just gonna set all these values, then we're gonna get them all, right? So if the tile value is not equal to U08 var, make a little error message. And boy, we have been really bad with this lately. We actually call it as a function expected, not actual. Let's figure out EVA, expected versus actual. Sure, why not? Okay. And we've still screwed something up here because, oh, yeah, because we're not making any sense here. Okay, so that looks good for a first draft. Do we want to explain what the heck is going on here? I think that an explanation might be useful. So, another set of tests. Get, put everything, then manually get everything. So it is like a put get test, however we do not use the So, when we do this test down here, we're going to manually fetch the values, right? We're not going to use the getter function. We're going to use the putter function because that's what we're testing, but then we're not going to use the getter function to verify the values. We're actually going to do our own kind of bit hacking down there to verify the values that we put are actually the values that are actually there when we inspect the binary values that are in the array. So let's make a note of this, say what time this is. So at vid IID, so the video is 82, and the time is 1 hour, 48 minutes, and 46 seconds. So well, we're back to that style again, I guess. So yeah, yeah, just explaining what's going down here. Right, so that's what we're explaining, right? Okay. So yeah, so if this works out, if all this stuff works, then I'll be confident that the bit packing functionality is working, that there's no problems. Let's make a note here that so this test index put all values for current test. So we're going to put all values to the current test, and then we're going to get all values. Right? That's kind of how we're separating this logic. So we have these two for loops, right? Both going through the offset dex. The tile value is looking up from the table, right? So the base, right? Okay, that's good. Now this base, does this base value need to be recalculated for both of these, or are we kind of like, this really looks like it should be something that's calculated out here, right? Because it's the test index. Yeah, so this is kind of like, you don't have to calculate this twice. It doesn't really matter too much, but we should probably put it here if we want to have our code kind of organized well, I guess. So the base is test index times the number of elements, right? So the stride times the test index equals the base offset. The offset dex, and the offset dex is lined up with this test table, right? So the offset dex should not exceed the number of elements minus 1. So we could also make an assert for that as well. I don't think we have to. I mean, you know, we could do this. Assert, right, the number of elements. We're just doing another assert here, aren't we? This is a define, so we could just do 16. Yeah, this is kind of pointless, what I'm doing here. But sure, why not? Max index equals the number of... Okay, you know, if we're going to do both these as asserts, it's going to get confusing if we don't do both of them. So let's just do both of them again. So the number of tests is 12. Right, so we know we're going through 12 tests. The maximum index is this 12 minus 1. Yeah, let's just put both of those asserts there again. Okay, so we're going to put the... Now, for doing stuff like this, we probably shouldn't do this weirdness. It's just going to confuse us, honestly, and then we're going to be like... yeah, we should probably just break this apart and not do this write code that weird. So just set global component equal to 0, right? I know we can do that in C code, but we should probably avoid kind of tricky stuff like that in our C code, because it will, when the tests break, right, and we're trying to figure out the problem, we don't want to be like, maybe it's this weird syntax we've done, right? We don't want to have to consider, we don't want to have that in our consideration. So let's probably not write the syntax weird like that. So let's take tile value and extract it as well. So instead of doing this assignment here like this, we're going to just say tile value here like this, right? So tile value is assigned over here, and then same thing with the global component index. CPU pixels is the same for the whole entire set of tests, and the This tile value, okay, so that looks good. And we probably have to do that in the, no, we don't have to do it here. So you see, we're using the put function here, but then when we get the values, when we do the get loop, we're not using the get function. We're actually kind of rolling our own bit unpacking logic and making sure that what's there is actually there, right? Because this is just the test for the put function. And because it's just a test for the put function, we don't want to use the get function in here, because we don't want this test to have failed because the get function was wrong, right? So we can't use the get function of this to write this test. Now later, after we've tested the get function and the put function in isolation, we can then use both the get and put function in another test where we integrate both of those function calls and see if they work together properly. But for now, we're only testing the put function, so only the put call is going to be used. The get call, we have to just use the basic bit logic that is inside of that call to write the test. So with that, I think we have the beginnings of what is a test. We can get rid of this error or whatever the heck, because we're done writing all of the logic, and we also need 2 more undefs for our what do you call undefs for our defines. They're local defines, right? They're local defines, and that means once we're outside of this function, we do not want to be using them anymore, right? So we need to undefine them. Sensible enough, right? Okay, so we got these 4 right here. Let's go up to the top as well and make a little checksum for that as well. And, or not, because it's kind of cluttered here. Yeah, I don't know what I'm going to do here. Okay. Yeah, so I'm sure that somewhere we've made some horrible mistakes. For example, we have this error thing. Why is this declared in the correct scope, or is error kind of a macro that is defined possibly at the top of here? So we don't want to accidentally make these local macros that don't need to be made, because if we do that, then we're going to accidentally undefine some things and break other tests. So it's very important that we don't accidentally redeclare things if they don't need to be redeclared for this section. And this is out of hand here, because we got a lot of test code, and so when we're trying to make local macros, we actually want those macros declared very close to where the code is being used. But here, with all this test code, it seems that if the error macro is declared up here, that's not very local here. Okay, so we got all these types here and whatnot. So that's telling me that for all of this test code here that we're writing, we don't need any type of local defines for the different types or the different logging functions. That's already kind of glued to the head of the function, and that's fine. But oh boy, is it kind of getting kind of hard to keep track of because of all this different test code, and just it's ridiculous. Like, I've already kind of lost track. Like, I don't know if I haven't scrolled far enough. Like, just way too much code here. So yeah, just a lot of stuff here. Oh, that looks about right. That's what we were looking at, right? Yeah, this error thing. So yeah, we need to get rid of this. So define very specific defines here only. So because I almost made a mistake, I'm just gonna take this, make my own define for this section. Right, and I'm just gonna call it that, right? And then we could also do the same thing here, right? We could go, and it's kind of silly, right? But the idea is that we almost kind of put some bad defines in our code, so we want to know. A lot of times you see what was done in the code, but you don't see what was not done. So this is my effort. This is my effort to kind of document what was not done as well. So now that we have that there, we still have to write this as well. And this also has a compile time error message, so the other code isn't even going to run if we do not... now, we could just do this, right? We could get rid of this, and now it'll compile, right? And then we'll have just this to-do message when we get to this test, right? That might be the way we want to do it. Just make a more unique message there. And I'm sure we've made some mistakes, so let's just give it a run and kind of see what else we've screwed up here. So, number of test elements undeclared in 4,700. So up here. Oh yeah, so times number of test elements. Well, it's not times number of test elements, right? It's whatever test we're looking at. It looks like we're looking at the first test. And the number of test elements is just called num test elements number 1, right? And that's because we refactored that, and we probably just missed that location when we're doing that refactor. Okay, so glowcom equals unexpected. So we forgot something, and oh yeah, pretty basic, right? And yeah, so we're just going to keep on running this until it... No way, is it already working? Because that would be shocking. Okay, so I'm kind of shocked because we wrote a lot of code and I only had a few syntax mistakes. But oh, alright. So glowcom not divisible by 4, bitpack put. So we have this little error here. Not divisible by 4, that is a problem. So let's go look that up and see what's going on here. So 0 is not equal to glowcom modulus 4. Now, is that the correct way to see if something is divisible by 4? It's the remainder of divided by 4, right? So we would get 0 all the time if it's divisible by 4. And we want a value that's divisible by 4, because if it's not divisible by 4, then it's not a proper component index. So I think we made a mistake somewhere in our test code. This is the put function, and we weren't getting this before, so I believe it is in our test code. So let's just say, you know, printf and let's say glowcom and %d \n, and then the glowcom, right? So that's kind of what we're concerned about. And we're pretty sure that it is the test code we've written that is doing this, right? We're pretty sure that that's what's going on, that is this test code. So what it would be good to do is say, well, right, so it's probably going to be one of these numbers here, but we can also do like a little log message over here. So in the beginning of the function, right, we could do a log and take the name of this and just say, you know, we're beginning the test for this. We have enough room where we could write begin at both sides like that. And then we need a null pointer for our logging function. And then at the end of all of this code, we can also make another message to say, to log that we are exiting this function. So not down here, but right here. Instead of saying begin, we will say end, because we're ending the function. Let's give that another run and just kind of see. I'm going to guess it's probably like the 12. Maybe that's not 12 times 3. I mean, that seems divisible by 4, though. So I'm not really sure. So maybe we're unpacking values improperly. So global component equals 2. Yeah, of course, that is definitely wrong. Now, the question is, how did we get that? Because if we look at the global components, right, we have 0 and 4 and 8 and 12, right? We don't have a... So what could be happening here is we're not doing we're not unpacking these values correctly, right? That would be a reason why we're getting this 2. Like, the 2 is probably coming from over here. And if we look at the logic here, is this the stride, the number of tests? And the answer is no, that is not the stride at all. Alright, so it's TI, so it's TI times stride. Right. That's what this actual calculation here. It's just it's this times stride. That's actually what we're doing. I don't know if that, I think that just makes it harder to read. So TI times stride, right? So we can make a little comment there that, you know, we're multiplying by stride like that. I think that looks a little bit better. Now, that does have me concerned that we may have done the wrong thing over here as well. So if you look at this, the number of elements, that is actually correct. So we've done it correctly here. We just didn't do it correctly on the previous thing. So if we go up here, now you have number of elements on both things. Okay, so let's give this a run and test it out again. And we're hoping not to get that error again. We're hoping that with a test, well, actually, we're hoping nothing fails, right? We're hoping everything just magically works, but we know it's not going to work. Put has failed, blah, blah, blah. So let's copy this, and let's look at where that is. Okay, so we're failing the, is it the first set of tests? Okay, so that's interesting. So it's the first set of tests, which is actually nice, in a way, because it could mean that our bit packing logic is so incredibly wrong that it isn't even, what do you call it? There's no memory stomping, right? There's no memory stomping, it's just that we just can't pack the correct values into the bits. So with this message, we have to think, well, okay, we have this message, so now that it's here, we might as well print off more information here, right? So, first thing is, you know, what's this variable, what's that variable, right? We want to just get all the values and just take a look at them and be like, well, what are these values? What else do we want to look at? The test index would probably be a good idea, right? Because without the test index, we don't know what test case we need to look at here. So let's take that as well. So the test index is TI. Okay, so we have enough stuff to where when this crashes again, we're going to kind of see, well, what case do we crash on? Do we crash on the very first case? Did something pass? Like what do we have here, right? So the test index is 1. So the first case didn't fail, but the second one did. So the U8 variable is 0, and the tile value is 1. Let's look at this. So test case 0, and then this is tile value 1 right here. So the tile value is the expected value, and this is the actual value, right? So actual not equal to expected. Right, so this is basically, this statement is basically saying, you know, actual not equal to expected. That is what it means. Okay, so now that we know that, what can we do to fix this? Like, so we think that, is the bit packing truly wrong, or is it like, or is it just that we don't know how to unpack? Are we improperly unpacking it, or is it just not correctly packed in the first place? So, that's kind of the tricky part here, and we gotta kind of, somehow print off, if we really want to inspect it to know which one's which is the problem, we might want to so my thought is, what about endianness? Does endianness affect this? I don't know. I think endianness might affect what we're doing here. But I'm not sure. Yeah, I'm not sure if endianness would affect this. But yeah, we have a value of 0, we're expecting a 1. So what could have happened there? Well, one thing is, maybe the value didn't persist, we didn't correctly set it into the actual data. That'd be one thing. Now, taking all these bytes, ORing it, 0 OR with all these things, that gives us a value. Take this value, shift it by the offset dex. I mean, that looks proper to me. So the next thing I might want to do is say, well, okay, we weren't able to get it. Is there the potential that this that it's all zeros, right? Because we're getting this 0 here. Is possibly the entire array all zeros? That's the next thing I want to check. So let's figure that out, right? So let's say for int32 chk equals, I'm going to say I equals 0. I is less than or equal to it's actually 4 times 4 minus 1. So I should actually loop through every single pixel. So if we look up here, we see that the CPU pixels is 4 times 4, right? So that's how many bytes we have. Let's see if there's the possibility that, for whatever reason, we tried to set a tile value and the entire thing is all zeros, because that would give us some information, right? So, so we're going to say, like, okay, so we'll say, you know, if CPU pix with the index is not equal to 0, so 0x00 not equal to CPU pix. We'll write it that way so we don't make any mistakes. And if this is the case, then nz++, right? We have a non-zero, right? So let's do a printf and 1, 2, 3, 4. So if this whole thing ends up, if nz ends up being 0, if nz ends up being 0, then that gives us some more information. Well, it's more information no matter what, but if it's all 0, then that tells me that the put function itself is wrong, right? So that means our fetching logic isn't wrong. It has to be the put function because everything is all zeros, right? So let's take a look at that, give that a shot, and see what happens. Okay, so nz is 1, right? So that's telling me that the problem could be in our bit unpacking, or it could be in our bit packing. We haven't narrowed it down, right? Because this tells me that one of these bytes is non-zero. Now the next thing I might want to look at as well, which one of the bytes is non-zero, right? So So since there's only one non-zero byte, we could do int32 index of last nz, right? We could do index of the last non-zero one. So we could say nzi equals I. So we'll just take we'll say this, and then we'll do a printf we could print this off like that, in case there's more than one later. And we can say, well, what bytes are affected and have this non-zero in them? Because that would also give us some more information. So we see that, right, there's one non-zero byte, and the current non-zero is 3. So that's 0, 1, 2, and 3. So R, G, B, and A. So the A byte, okay. So if we look at this, tile value of 1 and the offset dex is 0. If we look at our diagram in our PAINT5D data, we're going to notice that for offset dex 0, we are, in fact, in the alpha. We're in the alpha area. Right, so that's index, because we're going this way through the bytes, right? So we're going this way through the bytes, 0, 1, 2, and 3. Oh, maybe we did pack that pixel together the wrong way. So let's look at how we're packing this. Well, this is the red. It shifted all the way over, because we have this red, right, and it shifted all the way over in our bits, and it's the first index here, right? The second index shifted over even less, so second, third, fourth alpha is 0, right? So alpha has this, alpha has the greatest offset, but it shifted over 0. So the actual byte that we're looking at looks correct. So the next question is, well, do we have the correct byte pattern in there, right? So so let's do a so if we print off some hex here, so a hex value, not a pointer. So let's do hex pixel. And we're going to take, let's call it pix. And I'll call it, U32 pix equals, right? Or we could just do pix like this. I don't know. So let's give that a shot and see. Well, it looks to me like our bit unpacking, our actual test function code looks improper, but I don't know yet. So let's actually look at what does when we print out the hexadecimal value, what are we getting? So the hex is not very good here. We actually want like 2 places. And I think to get that we need, I think it's like a %3, 30, like that. I'm not sure that's quite right. I'm gonna break things. Yeah, that's not right. Okay, so this is not right. So a hexadecimal, let's look at how to print hexadecimal really quick here. So, okay, so in C, there should be a specifier for how many digits we need. So I know it's %x, but how do we get the number of places? Oh, %.2x? Uh, 02HHX? Is that what I want? That actually looks correct. Cutting and pasting from Stack Overflow. Alright, let's give that a shot. So we're expecting, 2 places. So I don't know if this is 0HX. I think they're full of shit here. Yeah, 2.2. %02. So I think I just need like 02. So like this, then I just need 02 like that, I think. I think that's how I have to do it. We're expecting leading zeros, right? If we don't have leading zeros, then we have a problem. So now we have... Okay, so now we have something. Now we have something we can work with. Okay. So the pixel value, the actual binary value in there, is just it's just a 1, right? It's just it's hexadecimal 1, and we're storing. Are we storing that in that location? And so if we look over here, we have this the second test, right? The tile value is 1. So that tells me that it looks to me that everything is actually encoded correctly, and that when we have fetched the value out of here, somehow we're not doing the math correctly. Another question is, well, why? Why is this improper? What have we done here that is not correct? So the first thing is, we know the OSDEX should be should be 0 for this test. So I really don't know what's going on here. Because everything points to it being 1, and right when we look at the actual data, it's there. So what are we screwing up? Eight plus 8 is 16, plus another 8 is 24, right? Yep. We're ORing it together. Bitwise OR. Now... Is this not correct? Is this logic somehow flawed? So we're assuming that this value is that this is a 1 here, and that all these other things are just... So it might actually be helpful to know what the U32 variable is, right? So did the U32 variable have anything in it, or where is the math breaking down? Because we think that, we're pretty sure that it's not the function itself, but it's our unpacking logic, which also means that if we've written it wrong here, we probably wrote it wrong in the get function as well. But the U32 value, what's in there? So the U32 value is 24. Does that make sense? That actually doesn't make sense, does it? Because the hex value here, there's just a 1. So 24, so let's look at a calculator here. So it seems like the way we're unpacking things isn't quite right. So we're expecting this, but we're getting like a 24. So we're getting like 1 bit. This is decimal 32. This is 16. How the hell do we get 24? So we get 24 by setting 2 bits here and here. Okay, so that doesn't make sense. So it's saying, you know, this first byte we're looking at, the bit's in the wrong place, and then the second byte we're looking at, there's a bit that doesn't even belong there. That's how we get 24. So I guess the question is, this U32 variable, we're expecting this U32 variable to if it's done correctly, we're setting a value. And then we're making sure that it's zeroed out. Yeah, so when we set the value, there's no way that there could be ever more than 2 set bits, right? And this tile value, there should only be 1 set bit, and we're kind of seeing 2 set bits somehow, and I don't know how. So what we're going to do here is we're just going to print out more stuff, I guess. So what the heck is with this? So why are we getting more? So So we need to figure out, well, why is this? Because I don't understand what we're doing wrong, but we are doing something wrong. I don't know what it is yet, though. So let's just take this and kind of paste it. 0, 1, 2, and 3. And then kind of take a look at that and be like, where are we making a mistake with the values? And we keep on screwing up our bit shifting, and the compiler does not like to correct us when we screw up bit shifting, I've noticed. So we're probably doing something very stupid somewhere. So yeah, so 0, 1, 2, and 3. So it's this third thing here that has a value, and that's actually what we expected. But what we're not expecting here is that this U32 variable, we're not expecting a 24 here. Like how did that happen? Because a 24, right? A 24 requires more than one set bit, right? Because it's not a power of 2. So what about our shifting logic? Is our shifting logic wrong? Are we kind of like shifting by these big numbers when we shouldn't be shifting by those? Well, I mean, it's 8 bits per byte, right? So that would make sense for what we're doing there. Yeah, I really don't know. I'm actually kind of stumped here. But I kind of expected that something was wrong with my bit shifting math, and now we can see that even this most trivial bit shifting thing, once again, we're getting very trivial bit shifting logic completely wrong somehow, and we're looking at it, we're just staring right at it, and we have no clue what's wrong with it. And that's kind of why we have the test for this, because look how easily we can screw this up. We almost need like a checklist for bit shifting logic so we don't screw things up. So somehow we run this, and you know what, we're just gonna have to bite the bullet here and just say count bits. Okay, let's count the bits, right? So let's do so less than or equal to 32, right? 32 bits, or less than or equal to 32 minus 1. And I don't know if we should really be using bit shifting math to check, because we already kind of proven we can't do that correctly, but let's try anyways. Alright, so we'll just try, like, Alright, so we'll create this, you know, bit counter thing. Bit count. And then we'll loop through all 32 bits of the 32-bit integer. We'll shift everything over to the right, and then we'll mask it with a 1 to look at that individual bit. Right? And then it's either going to be a 0 or a 1, and we'll add it to the sum. That's how we're going to get our sum of number of bits. And it needs to be, if it's greater than 2, then we have a problem, right? Because they only... Right, we only have 2-bit values that we're encoding, so if in this test we're setting a single tile value that's only 2 bits, then we should never get anything more than 2 bits in this little count here, right? So let's make a note here of what we're doing here. So at vid iid, and say 8.2, and the time is 2 hours, 34 minutes, and 48 seconds, right? So right here at this timestamp, what we're doing is we're counting all of the bits in this U32 variable that we've kind of globbed together. And we're making sure that there's not more than 2 bits set, right? If there's more than 2 bits set, we have a problem, right? So we'll shift by 0 to 31 and mask with a 1 to get the 0 or 1 bit, and then add that to our total here, right? And we should only have 2 1 bits in the whole entire uint32. So let's give that a run and see if that crashes, right? And we think this is going to crash, but we want some sanity of mind to be like, well, maybe we just reported the value wrong when we were debugging, and maybe we actually only have 1 bit, and we just don't know what we're looking at, right? So if we look at this, yeah, so we still have this thing that says we failed. So the U32 variable still says it's 24, even though we have not gotten something that says that there's too many bits set here. So has the U32 variable been changed since then? So I think that what we'll do is if U32, we'll just do this. If 24 equals U32 var, is that not out of range? 24 is a bad U32. Well, is 24 24 is not necessarily a bad number, though. 24 is bad in the sense that, okay, well, let's look at a calculator for a second. So look at a calculator, and if we do decimal 24 and then look at the binary, we have 2 bits set, which is actually does not exceed the number of bits need to be set here, right? It's not what we expect, because we don't expect there to be 2 set bits here, but somehow that has happened, right? So we got this 0, we got this 0, and then we got this 1, right? That's the values, and then somehow doing this, we have somehow encountered 2 set bits instead of 1 all of a sudden. I have no clue how the hell that is, and it's kind of annoying me right now. So it's kind of obvious to me that we don't know bit packing, right? We don't know bit packing, we don't know what the hell we're doing, and so we might want to take this and make a little demo sample to see, well, what we're doing wrong, right? Because we've already kind of figured out that something here is completely wrong. We don't know what it is. It's annoying us. So let's rerun this calculation here. So we know that these eventually end up 0, 0, and 1, right? So why not take this well, no, we want to take this, right? And we have a 0, 0, and a 1, right? These are all 0s and these are 1s, according to what's over here, right? And so we're looking at this, and we're expecting this to be, Alright, so we're thinking that if we actually know what we're doing with bit shifting, then, you know, this is what we're expecting, that these values, this is what they end up being, 0, 0, 0, and 1, and so we're shifting over these amounts, and we're ORing with this, and we're expecting to get back a value that's just 1, and somehow we're getting 2 set bits. We're getting a 24 somehow. So let's give this a run and see, does this end up crashing as well, with a error message of you don't know Jack 2021. So let's kind of see what's going on there and see. Yeah, because it seems like we don't know. Yeah, we don't know Jack 2021. So something about this is not what we expect at all, and that's kind of infuriating. We do expect that it probably means that this test, my understanding, is 24. So we don't have much room. We're just kind of working in some very clustered quarters here. TMU will be for test my understanding. And, so I'm going to bet you that this is 24. I bet you that we're going to see a 24 for this. If we didn't make any syntax errors where we kind of... Okay, so I don't know Jack, and the value is 24. So we got 0, and we shifted it over. Oh, hold on. Okay. Because it's the wrong way. Because we're not doing this right. We're not... Yeah, I see. Okay, got it. 24 shifted over. This is 24 shifted over 0. This is 16 shifted over 0. This is 8 shifted over 0. This is 1 shifted over 0, right? So, oh, this is 0 shifted over 1. So we have 8, 16, 24, right? If we take 8, 16, and 24, shifting them over 0 because we don't know what we're doing. Well, where's 8? So there's 8. Here's 16. I bet 24 is here. Yeah, 8, 16, and 24. That's these bits right here. Okay. So we know this is 24. Make sure your shift amount Okay, so the problem is that when we wrote our code for the unpacking, we put the shift amount on the wrong side, right? This is, yeah, so we put the shift amount on the wrong side. That's what we did. So over here, where we're kind of trying to shift this out, we want to take these values. This shift actually belongs over here. Right? The amount to shift actually belongs on this side. Now, does that work the same way with the shifts with the other direction? I don't know. Obviously, I don't know how to bit shift. I need to do more bit shifting. So, that was a pretty stupid mistake. Well, we do want a left shift. Now, the question is, did we do that over here as well? Yeah, we did the same mistake over here. So let's take this stuff over here, and let's paste it over here. And, yeah, this just fucking sucks, man. Okay, so, yeah. So, we fixed that shifting logic, and let's kind of see what happens now. So it kind of sucks that, you know, we looked at this and then we had to conclude, I just don't know how to do bit shifting, right? So, to do blue barrels full of grapes. Okay, so interesting. So that's telling me that all that test code passed. That's crazy. To do blue barrels of grapes. Yeah, we got all this test code, right? All these different cases, and we manually checked them, and we know that, you know, this, we're pretty certain that that's working, right? But before we even write the test code for this, we know that when we did our bit packing and stuff, and we're looking at stuff, we were like shifting in the wrong direction. So it might be advantageous for us before we even write the test code to just be like, hey, for this bitpack get, are we perhaps shifting in the wrong order thing? Doesn't look like it. But now I am kind of scared. I'm going to assume that this is, you know, this shifted over by this amount, but now I'm like, I don't know. Is it like inverted? I don't think so. Let's make sure that we know how to write shift properly, right? Because we made this mistake, so we might as well say, hey, how do you write, let's put it over here, write shift C. And so my question is the amount to shift always on the right-hand side? So here's our left shift and the amount to shift, right? And we know that that is proper. Now, what about shifting the other way? So we got this A shifted over 1. We got the B shifted over 1. So yeah, the amount to shift looks like it is always on the right-hand side. A and B. B. Okay, yeah. I mean, judging by the sample, yeah. So we are shifting correctly there. It's just that we need to yeah, I mean, yeah, so we just have to write another piece of test code for the next thing and see what we can do. I'm actually surprised that all of those test cases just worked. Blue barrels full of grapes, yeah, so and we kind of know that that for these test cases that we're fairly certain that the test cases are in fact running, because we had one of the test cases fail. Now what we could do, let's just mess something up really quick. Instead of a 3, let's put a 2 here. And we're going to expect that to actually cause a crash, right? If that doesn't cause a crash, then I'm going to be concerned. So let's just throw that in there and just see if that causes our unit test code to crash. Yeah, so now we have a problem. The expected no longer equals the actual. Okay. That tells us that our unpacking math is actually important to the success of these tests. So I am kind of worried because I wrote all these test cases, only had to check my bit unpacking logic and fix that, and then bam, everything just works. And that's kind of disconcerting. I know it's kind of weird to be like everything works and therefore I'm paranoid, but that's kind of how I am here. Just because it's so much code that I thought it would be much more effort to get all of that working. So I think that we have actually written this first test here. Like this test up here, we're done with this test for figuring out the pudding, and now we need a test for the, we need a test for, the get, right? That's the next thing we need to do. Now, everything is in a order where it's compiling and we're getting this message, so it's a good save point. So let's do a git bash here and just kind of save what we have. To do we'll commit that to the private repo because it's still not in a good enough state to commit publicly. Yeah, so I really didn't want to do any work. I just wanted to get a little bit of work done to say, hey, at least I did something today, kind of a thing. So, I mean, about 3 hours worth of work, that's actually pretty good. I think that before we give up here, though, we should probably get some more exercise. We did like our 100 push-ups earlier. Technically, that was yesterday because it's now 1 a.m. So, I think we should at least do 30 push-ups, 30 crunches, etc. Because we said for every hour, we want at least 10. And I think that 100 of everything is going to be a little bit too intense. But let's just do our push-ups and whatnot, and then get out of here. And, yeah, so let's do our push-ups, and then we're out of here. So, let's kind of find that. So our push-ups, we've already done 100, but that was technically yesterday. It's now Sunday. Sunday I'm actually not supposed to work, so so now that it's Sunday, oh no, did we not change the recording number on here? Wait, no. Oh, no, we didn't break that. It's just that we started on Saturday and we rolled over after midnight. Okay, so that's good. Okay, oof. I've been trying to be really good at making sure these are the correct numbers here because... Okay, so I guess we'll just say that this belongs to, even though we rolled over, we'll just say that this is still Saturday, and we'll just do like 30 more of everything, and then once we're done, we'll be done for today. We'll end the stream. But the stream is basically over, but I wanted to, I want to, like, I don't know, if I don't do my push-ups now while we're on stream, then I'll never actually do them. So, one more thing before we go, though. We need to take all of that debug printing code we wrote, and we're printing off the hexadecimal. That was actually a decent reference here, this 0 to X thing here. I'm going to copy that. Actually, I'm going to copy this whole thing here, and I'm going to put that in my notes for how to print off a byte. Okay, so just making a note of how to print hexadecimal with leading zeros, which is on line 4861. And did we change anything while we did that? We shouldn't have, but let's just check. Okay, nope. Let's give it a run, right? Let's just have some sanity of mind here before we start doing our push-ups and whatnot. Okay, looks good to me. Yeah, so I really don't want to write any more code, so let's do... Okay, so everything looks good in our code, so let's just start to do push-ups, and then let's get out of here. Push-ups, crunches, and all that other stuff. 30 of each. Okay. So we did 30 of everything. I can change that to 130. I think we're done. Okay, so we're still doing test code for PAINT5D. We're doing bit packing logic. We're doing the tests. We'll do the other test, I don't know, another day. Maybe on our caffeine day. Right, we know where to go next. But yeah, we just got to keep on going. Write the git test, and then write more test logic to figure out where the problem is in our code. But hopefully you can get all these tests. So what happens after all of the tests are written? The next part is we actually need some type of mechanism for taking the coordinates of the client area, so the actual client area mouse coordinate, and we need to be able to use that coordinate with the brush to actually set data onto the GPU tile map. And in order to do that, we're actually going to need to make even more functions than I originally thought. There's just a lot of pieces here, but this is just ridiculous, isn't it? It's like this one system, right? There's almost almost 7,000 lines of code in here. More than half of that is just test code. And also, we write everything very verbose and linearly. So, you know, my 1,000 lines of code might be your 500 lines of code. By the way, I just write everything. But whatever, there's a lot of code in here, right? So we're done. I mean, also, you know, lines of code isn't the best metric, but I think it can be used as a rough metric for yourself. Like, if you know how you write code, then you can compare those metrics against yourself, but it doesn't really work very well to compare that metric against anyone else, right? If you write code of a very consistent quality and a very consistent density, I think you can use that for yourself. You just can't use it for other people. Anyways, I'm out. See you later.